Hello and welcome to my new video on Nintendo 3DS low-level 2D. In this video I will expand on the previous video and show how we can combine both screens to form one to make a larger surface for our games. So, as I just said, this tutorial will build upon the last one. We'll be extending, or rather I will show you a new blit function which allows both screens to be treated as one, and it will copy pixels from our images to either frame buffer, which it will determine which one to draw to, or draw to both if it needs to. For example, if there's an image overlapping the seam between the top and the bottom, then part of the image will be drawn to the top and then another part will be drawn to the bottom. So if you've not seen the last video, one thing you should note is the weird way that the 3DS stores its screen frame buffers. They're rotated by 90 degrees, and the origin before it's rotated can be considered to be at the bottom left of the screen rather than top left, which is normal for most consoles. So when we work with both of the screens, one of the issues we got is this top screen is 400 by 240 pixels in size, and the bottom screen is 320 by 240. So what we need is a common size. So what I've settled on here is 320 by 480 to be our main sort of game screen size. So what this will actually mean is we will have 40 wasted pixels on either side, like a margin, if you like, with the center area of the top screen being aligned with our bottom screen. The function we'll be using to draw to these will be called Blit2Both, and what this will do is it will treat our new 320 by 480 frame buffer as being one large image, and then you can think of the origin of this image being at the top left, and we will code away the differences between the DS and the 3DS and many of the other consoles out there, so we can concentrate on coding in a uniform way. So let me see, as I was saying here, we'll have a unified screen, and I think the best way to demonstrate all of this will be with a game. So first off, I will show you the game. So what we have here, this is the top screen and this is the bottom screen area here, and you'll see here we have a margin on the top here. So when doing games using the large screen format, what you'll kind of need to do will be to just draw some other image on the top here to fill this unused space, if you like. So if you were kind of really creative, you could think of some sort of display to kind of put in the borders here to make it less noticeable. So this game is a maze game where you have to collect coins and avoid enemies. Currently this has 2 players. You can be either Vic or a Viking. And then what we have in the game is we have two different AI types for the enemies. We have a left and right movement and an up and down movement. When they collide with each other, this will affect their movement as well, so they will bounce in effect. And then what we can see here is the top screen and then the bottom screen here, so this gives us a larger play area. And then at the bottom here I have our heads up display information for the level here. We have our score, then we have our collectibles, the rings, how many there are to collect. These are our lives, and in this game engine that I present to you, there are currently 2 levels. I have updated these levels. The first 2 levels are kind of designed were a bit too hard, so I've simplified them. But the source code I provide to you will have the original levels in, so you can put them in and see how you do with those. So I'll get into some things about the game here. So this game best demonstrates how you can have a larger display using both screens. I thought the coin dash game would be something more interesting for you to dive into and play around with the code, so you can see what you can actually produce with it. The game pretty much is complete except for a lack of content. Obviously there's only 2 levels. There are currently only 2 enemies, but I will show you how to add another one in a moment. I will also show you how the levels are made, and I will also show you how to add another enemy graphic as well. It's basically there for you to extend and dive in and see how it all works. So in our level, if I just bring up one of these levels a moment. So the level design is designed in LibreSprite here. Obviously you can use whatever pixel editor you want to use. So each tile represents a 16 by 16 pixel image on the screen. And then if I move these side by side a moment, so the black areas are empty space. This is kind of like this palette at the top here, which I include. I use it as like a key template, if you like. So each of these colors here basically represent a different thing in the actual game world. So the white pixels in this level are walls. So these colors will be 0 to 4 here. So white is a wall. The green color is where the player will start. The red pixels are the enemies that move sideways, and the purple pixels are the enemies that move up and down throughout the level. So this makes design in levels pretty simple, but you obviously need to have an idea of the size of everything in your game. So if I jump back into some of the other graphics here, these are the wall tiles. Obviously you can add more of these, maybe have a different wall tile for each level possibly. So one thing to note is everything in the game is expected to be 16 by 16 pixels in size, except the floor tiles. These are larger. As you can see here, we have two different floors, and then whichever one we're using, we use a different one for the border. Again, there's no reason why you can't extend the amount of floor graphics. Some of this will be, obviously, if you change the size of some of these things, then it will be trial and error for you to get everything working. And then we have one image here for if you collide with an enemy. And then currently these are the enemies in game. We have the fish that moves up and down and the bat that moves left and right. What I will do in a moment is I will show you how we can add another baddie. So we'll have our crab here, and then we will also add a new selectable player here, our dragon. So what you will also need, as per the previous video where I showed how I was creating graphics, is you will obviously need the DS to tile program. So I'll just wrap up with some more of this a moment, and then we'll convert some graphics and then jump into the code. So like I was saying, the game code is pretty much complete. One thing it is lacking is there is no option to pause the game, but that would be pretty simple to add in, as all the states in the game use a state engine sort of design pattern. So it's just a case of dropping another state in and then putting a function to deal with it. One thing I will mention here is obviously if you're watching this video but you're not actually intending to code a game yourself, maybe you would like to test out this game on your 3DS or 2DS, then let me know below in the comments, and I will look to extend this demo with a few extra bits and pieces and then put it on itch.io for you to have a play with. So one of the things we'll do now is I'll show you how we can add in some new graphics. So for this you will need the DS to tile program. And then what we'll do is we will convert the characters into 8-bit graphics, and then make sure you choose to get the image palette from the actual image itself. And like I said, everything's 16 by 16 pixels in size. You will need to obviously put in a size and then just drag and drop your graphics over. And then save that as a C file. You always need to make sure you put a size in here, otherwise it will treat it as being one large image, and then all the pixels will be read from left to right and then top to bottom. So let's do the same with our new playable character. Okay, so we've got these. So then just open those up in a text editor there, and then we'll need to create this is going to be a problem here. What we'll actually do is we'll just extend these, otherwise there will be we'll have to switch out color palettes. This is one of the problems when you're working with 8-bit graphics. Obviously they didn't really need to be 8-bit, I could have converted them to 16-bit really. But as there's only a few colours in these, I didn't see the real need to sort of do that. So all this alleviates is working with the sort of changing the different color palettes. So open up our players now and do exactly the same there. This also means we can update all of this in one go. So back to 8-bit again, and then we'll grab the palette from the image. So we'll change the players first. So we'll now change that to 3 types, and then the same for the baddies as well. And then as per my normal sort of way of doing things here, I note the various sizes of things here. So the floor tile sizes, the general whole game sizes there, 16, and then these are the images which we'll be using. And then one thing to note here is, as these literally are just a list of the starting locations of the first image for each of these types, if you've got more images in that sort of image group, then you'll need to add in how many of those are in that group as well. This will make sense in a moment when I explain it in more detail. So we already have graphics for our players here and our enemies here. So all we need to do is to just change those. So that's the players done there. Now that we've added all of these, let's just make sure I haven't hard-coded too many numbers in here. So that should probably be player tiles there. So what I did there is these here are how many animation frames there are per animation set. So what that means is you can see we've got 3 types, and then there are 2 frames per type. Obviously if you had like a directional animation, then you would obviously need to sort of change all of this there. That's the same with the enemies as well. For simplicity in this, they only have 2 frames of animation each as well. So the reason why I try and template everything out here with these is so we can easily sort of change things in one place, and then the whole game picks up these numbers if it needs them using these variables from here. So we only have to change things a few times. Okay, that's built. Let's see if things work okay. Okay, so nope, that's not working there, so we will stop that and jump in. Okay, so that's also defined in our player header as well. So we now need to add in our new player as well. There we go, that should sort that out. There we go. Oh, his feet aren't moving. Oh well, we'll let that slip through here. So let's get through to starting the game. Okay, and he's appearing invisible. Okay, so there has to be something in the player there. So we set our type in here. Okay, what am I missing here? This is a problem with live updating things. It's weird though. It's never. Okay, that's weird. It's been replaced as a background tile for some reason. Okay, I figured out what the problem was. I'd interchanged a start here. So when we initialize our player here in the player initialize, I'd put the tiles there rather than type. So it was calculating it wrong. So what this graphic start bit for our player does is it holds the number of the image at the start, which is our player type, and then that's then multiplied by the amount of tiles. So now that starts as expected. There we go, there's our new character. Although his feet aren't moving. So now let's look to add our new enemy character. Now one problem is we need to decide what type the crab's going to be. I'm going to put him as a moving left and right. So what I will also need to do now is I'll probably need to go through the baddie manager initialize function as well. So I'll dive into this in a moment. At the moment here, what I'll do is I'll just add in the new one here, so the left and right. Do this randomly. So what we'll do is we'll do a 50-50 coin flip, if you like. So let's have a look at the start here. So the graphic tile start. So as I said before, we have 2 tiles per enemy. Initially the enemy graphics was just for 2, so the starting one is the up and down and the left and right is the bat. But now what we are doing is we're saying the crab is also a left and right as well. So all we plug in into this variable graphic start is the start image, and then we have a separate variable in our actor type, which I will explain in a moment, which holds which individual animation frame. As all of them have 2 animation frames, the frame for them can just be 0 or 1. It's not really used, to be honest, in this game at the moment, as we have a global variable for the enemies that control which frame we're having, as they are all, their animations are all the same size. They all have 2 animations, so there's no reason to individually do this. Obviously that could be something that you do yourself, and then maybe add in like another variable for frame count or something. Anyway, the graphic tile start is the starting image ID. So for our crab, it will be 2 times the baddie tiles. Probably could have used better wording actually than what I have here to explain that. So let's see that in action now. Yep, there we go. Look, we have a crab down there and a crab up there. So that's how you can just add some extras to what we have here already. And now I think it's about time I jump into the code properly and give you a proper oversight of what's actually going on here. So first off, we'll go over the main changes between this video and the last video. So one thing I did was I moved out the image manager code into its own module, and I've also added some more functions in here. So we have 2 overwrite functions now. So the overwrite allows you to literally just in fact, I'm sure there's some issues with that. In fact, no, there isn't. No. So what happens is once we when we create an image, first off, we obviously have to pass across how big the image frame is. This is then stored in a list of images. Move this across here, we can side by side them. So here we have a static list of the image types here. And you'll see we have 512 as the static limit. By being able to overwrite them dynamically like this, we could probably lower that by quite an amount. So for example, although we have all of the sort of players as having separate images, we could literally just have a small range of player images and then overwrite those image numbers with our next player that we select, rather than having to load all of their frames in at one go. So instead of loading in the 6 images here, we could literally just load in 2 of them. And then if we changed player, we would then just copy the data for our next player over the top of the images we have in our array here. This is what these commands allow you to do. So you can think of, we have 2 floor graphics currently, but you could just keep those 2 in place. One could be a border graphic, the other could be a floor graphic, and then each level you just overwrite those images with new data, so you can keep the image number static throughout the whole game. That's what these commands kind of allow you to do. And then another thing I've introduced here as well is rather than having to keep redrawing the backdrop image, we have a command here which will allow us to first off, we can create an image. This one here will do it. This will create like a blank image. And then this command here will allow us to draw tiles onto that image. So for example, you can have like a level like we have in our game here. As the walls and floors are static, we can literally draw it the once to one of these background images, and then just draw that background image as the first image each time, which is obviously quicker than having to draw every tile for the level over and over again. But obviously that's only great for like static displays. If you had like a scrolling game, obviously you wouldn't want to use that. So that's just some additional things in here. So I will now go through pretty much everything else which I think you'll need. So one of the things I've done here is we've got global variables here for display width and display height. Like I said, both of the screens are treated as one image, 320 pixels wide by 480 pixels high. We have 2 sets of global variables here. These are used for collision detection. And then these here let's just double check that a moment that I am actually using those. Yes, I am. So one of the things I've done is I've created a load of orders which we send to the actors. By the actors, I mean the player and the enemies. And then they can be ORed together, hence the numbers are correspondent to bit flags, so they can move more than one direction at a time. So in the player structure, the player update function takes an order command. So the reason why I did this for the player is it means in the game module is where the input is read only, and then we build up what buttons are pressed on the controller when playing the game. So in this bit here, in the play state, we create a local variable here, PL move order, set it to 0 each update, and then if the thumbstick or the D-pad is down. So in this case here, if the left stick is down or the left D-pad is down, then we move order with the order to go left, and then same for right, up and down. And then if our player is alive, we first send the move order to the player update function, which handles the moving and animating. And then afterwards we check to see whether at this new location we've hit a coin by calling the level manager code. So I will first jump into main here. So the differences in here now is we have global game states. We have two main modules for game states. We have our game state module and our title screen game state. And then we have initialize and run for each of those states. So this is our main loop here, where we start off, where we set our graphics mode, and then we set up our double buffering. This was pretty much the same as in the previous video. And then you'll see this loop here is pretty much the main game loop here, where we update the input manager, check which keys have been pressed or not. And then if you press the select key, this will break out of this here and shut everything down. Otherwise, the game state will only ever be either in the title screen or in the game code here. So I find this to be a nice easy way to kind of handle the logic in all the games that I make. Just have a simple state machine for the main game logic here, and then each of these states, if you like, they can have their own independent stuff going on, their own states inside of them. So for example, in the title screen here, this includes the main header file, so we can change the game states from the title screen when we're ready. And then you'll see here the functions for title screen, init and run are defined in main, and then we just implement them in here. So here we have the title screen init function here. And then there's like two states in here. There is the choose your player state, and then there is the wait for you to start the game state. So most of the time these initialize parts are literally just called once, which is why for all of these initialize functions here, when I call it the one time, I update the game state from in the case block here, so that it automatically then goes on to the run state the next time round the loop. So in the title screen here, you'll see with everything pretty much, we always need to draw the backdrops first. So the top and bottom here, these are basically backdrops which we create dynamically. So if I get to the graphics initialization part here, as I was explaining just now in the image manager code here, these two functions here basically create these two images here on the fly. We basically create empty images where we will basically draw the backdrops for either sort of title screen, if you're going to have like a different sort of like a picture on there or something. One thing you could do is either load in an image and then draw that, or you can create these two backdrops, and then using the various Scene2D Blit commands you can then draw to them, which is why you'll see in the initialize function here, which is called once, we draw the floor and the border for the level only one time, and then we call the im blit backdrop function, and then what you have to tell that is whether you're drawing to the top or the bottom backdrop, and then you specify the image ID and then the horizontal and vertical position. So one thing to note with the blit backdrop functions is they do not change the origins for the screens. So both of the screens origins are actually the bottom left normally. When we use the Blit2Both function, it changes the origins and then works everything out automatically for us, whereas the other functions in S2D, for example blit top and blit bottom, they do not do that. Again, you'll have to play around with some of the code, probably get like a better understanding of how you can use these things. But basically the whole reason for the backdrop images are literally so that you can draw the scene once, or draw a scene, or even just draw to one image, which will be a global background image the one time, and then just either copy parts of that out or draw it as like a backdrop. So the floor here basically oh yeah, you'll see that there's also a Blit2Both function which also calculates everything using the origin in the top left, whereas if you use the other function here, then the origin will revert to the bottom left, not the top left. This is because this part here draws only to the top background, and this draws those borders. So for example, if I change this to that there and then run it, you'll now see that the left hand border is now just bats. So the image Blit2Both draws the main 320 by 480 region to both screens and does the calculation to put them in the right sort of place. Whereas the image Blit2Backdrop normal function takes either the top or the bottom. So note, you can only use these Blit2Backdrops if you remember to actually create the backdrops in the first place. Otherwise you'll be writing over the top of some of your existing images. So these are just ways to kind of draw the backdrop once without having to completely do it over and over again. So this command will allow you to draw to the unified screen, whereas this other one here is for working with either the top or the bottom separately. And then in here you'll see we have these same functions from the previous video. If you need to just draw to the top or bottom on their own, then you can call these, but they do not change the origin, whereas the Blit2Both treats the origin as top left. And then the print to both screens, again, that does the calculations automatically for you. So a hack that you could do with the Blit2Both is you can still draw to the outside areas of the top screen if you put a negative number in there or a number greater than 320, as the Blit2Both is just calling the Blit2Top and Blit2Bottom internally. Just seen an issue there. I forgot to remove them out of there, look. They should not be in there. Now the question is that going to break anything? No, happy days. Let's make sure it works as intended. Safe, that was worrying there. Okay, so that's just some stuff about the Blit2D from the S2D things here. So now I'll get into some other bits and pieces quickly. So let's jump into the level manager a moment. So the levels are set statically to 20 by 26 in size. So all of these currently need to be that size. So the reason why it's 27 is because there is obviously the color template at the top. That line there, obviously we don't copy that in. So that's the size that we need to be. We define that size in here. So if you add more levels, then that's the size that they need to be. And then in here we have the level count. So if you extend the levels by adding some more in, literally just copy the new sort of level, maybe extend it at the bottom here or something, and then just change the level count. And then you'll also need to change the maximum levels here as well. So one thing I'll talk about again with the levels, I just have to open them up again. Okay, so one of the things I put in these maze games here is you'll see that there's gaps missing at the ends here. So what that allows is that allows the character to wrap around to the other side. If that's something you don't want, then obviously you don't need to include that in here. You can literally just make all of these walls. However, in the if one of the actors moves outside of 0, which would be going past this here, or past the width in tiles of 20 here, then they'll wrap around to the other side. That's what this does here. It works out the width of the level in pixels and then subtracts the actor width. Which is why these exist here. So we know in the game how big everything is, so we can kind of try and template out everything as much as we can. So the whole sort of code is almost a game engine in its own right. And then some other things we have in here is, if you notice when the game runs, you see we have like an area at the top here where nothing's being drawn to. That's what this is. When we draw everything, we're also adding on this value here. So for example, if I go into the player render function here, you'll see the Y position of the player adds this value on. That's the same with the baddies as well. Where their Y position also adds that. So if you wanted to remove the top bit, you could literally just set that to 0 or something. And then, as I was showing in the beginning of the video here, the tile types are indicated by this enumeration here. And then we have kind of like a collision map, which is this here, which holds the tile ID at a location on the map. And then another thing we have in here as well is we have a list of starting positions for the baddies, which is this structure here where we indicate what type, and then the tile X position and tile Y position. So when we initialize a level with level man initialize level and we pass in the level number, we first work out which level we need to target in our level data array, which is in here. So in here you should have all your levels just linearly stacked one after the other. And then because we know how big a level is, we can work out how many bytes by multiplying these two together each level takes, and then we can skip to the start of each level, and then we can load a pointer to the start of that, and then literally take 1 byte out of there, and then use a switch block to set the tile type to put into the collision map. So when we start a new level, this will basically read over the whole map, and then depending on the number that it gets, it then works out, okay, is it a wall, a player, or an enemy? If it's the player, then we literally set the starting position for the player here. If it's an enemy, then we have a function to add an enemy in here. So this baddie start list and the start list count, they basically hold a list which can be filled of potential enemies. You see here I set it to 30. It's just a number I plucked out of the air. And then you'll see here we literally just set a new starting position with the type in here, and then add 1 to the start count of the baddies. So when the game, after the level has been initialized, you call baddie initialize, and then it basically looks at the level manager's list and then goes over it, and then it then converts the numbers in here from tiles into pixels, and then loads those into each baddie there. So we use the rectangle structure in the baddie actor. Here's the actor type I created for every character in the game here. We have a face and frame for which way they're moving, a frame which is basically like an offset number between 0 and however many there are in that animation set, and then a graphic start ID, which is literally the starting image ID, which the frame will then be added to at the end. And then we need to know whether the actor's alive. And then the rect here, we not only use it as the starting position, but we also use it for checking collisions between actors. As you'll see, we also have a function here to check for rectangle overlaps. So this is pretty much the a level initialize function here. You'll see that if we find a blank tile in our level, then we'll add a coin at that position. If there's an enemy there, we'll also add a coin as well to be beneath them. And then we set the collision map with the tile ID that we've got from the level data as well at the end of it. As the level manager, each update, it draws the floors. So it draws the backdrop there. And then it draws the level using the collision map. So one thing I didn't do here is you'll see that I didn't draw the walls onto the background images, which I could have done. I could have put that in there instead, but by not having the walls be statically drawn onto the level, it means you could actually animate the walls if you wanted, but you would have to obviously change, like add in a frame and a frame count for how many in the wall animation. So when we call level manager update graphics, it then draws the level, and then it also handles which frame the coins will be as well. It handles the coins in here, drawing the coins. As you'll see here, we basically crawl over the collision map. If there's a wall, then we'll draw a wall. If there's a coin, then we'll draw a coin. So another thing to note here as well is the coin itself has its own entry in here, which is number 5. Because obviously we couldn't just leave the empty number as being a coin, because otherwise we wouldn't be able to erase it when a player collects it. So now I'll go over the how we sort of collide with walls and collect coins as well. The coin will be the easiest one, so we'll go with that first. So the player never actually checks whether he's hit a coin himself. It's always done in the game. And then we check that after the player is moved. So you'll see in the player code here, we have a number of things which can be read from outside the player structure here. We have the player XY type and a function to get the collision rectangle, and we also have a state the player can be in as well. These will just be enumerations as well. So these enums basically allow you to sort of create state machines for them as well. So I would always have the dead state as 0. That way any other state above that means they're alive and doing something. So the player state, we want to know whether he's alive or dead from outside of that in the game here. So this is in the play state here. I won't go over every state. I will literally just pick a few which I think is of interest, and then allow you to kind of figure that out. So the PLX and the player Y position get set from the player. Each update, basically what happens is the player's actor rect X and rect Y get plugged into player X and player Y. And then we pass in those pixel positions into level manager, hit coin, and then those pixel positions are then converted into tile positions, hence they are divided by tile width and tile height. So then we can check those numbers in the collision map. So what this does actually mean is in the game it kind of it's a quick way to check for collisions, but it's obviously not as accurate as if we were using rectangles to do that, but it works nonetheless anyway. So all we do is if at that map position there is a coin, we clear it from the collision map. That has the added effect that when the graphics is drawn next by level manager, it will not draw a coin there. And then we subtract 1 from the coin count, and then we return a true result to say we have hit a coin. And then you'll see here the just increment the score in the game. If the coin count is 0, then we basically change the game's state to level up. I'll now quickly cover that here now as well. So in our game here we have a load of states for the game to be actually in, and then we have a sub-state for each of these states. So a sub-state basically says the state is in the initialize phase or it's in the run-in phase. You can obviously bung in more bits and pieces in there as you needed. And then we also have a load of global messages in the game as well. You can think of these as something generic for every game. You always kind of want to have like a get ready sort of a state or phase in the game where you're telling the player, you know, level's about to begin. And then there's usually another sort of stage where the level's cleared, and then there's a game over one and a game won. So these are states, and these are like messages associated with those. In here we have like a generic like message manager, if you like, which will print a different string of text at a certain location on the screen depending on what message ID it's been plugged with. This is a quick way to plug in like game messages to the player. So to get that working here, we have like there's like 2 tick timers. These are simple structures. We basically update these every sort of tick of the game, so they're not kind of based to any real sort of time, if you like. They're just based on updates. And then in here we have like a different timer constant values set for these things. So these are the core sort of things in the game. We have the level number, the game state, the game substate, the score, the lives, and these are just some miscellaneous variables used for things. For example, we have like the active message ID, and then the messages, they sort of blink. That's what this boolean handles here, and this is a boolean to handle ending these states here. So I'll quickly go over some things of importance. So in the game initialize, first off I clear any outstanding graphics in the blit lists from S2D, and then I set some raw numbers here. Obviously, if you want more than 3 lives, then feel free to plug that number in there. And then at the start, we have the substate and the main sort of game state. So at the start, we have new level, and then this then returns from here. And then the next time round, the game run, which is defined in main here, will be called, and it then has its own game state, which it executes in its own state machine here. So this makes things nice and modular. I mean, I could almost like draw this with blocks, showing where the logic goes. So to add another state, it would just be a case of a case and break, and then maybe add in like a new game state in here, maybe even new messages or something. It's fairly straightforward. And then one thing to note in here is all of the HUD positioning numbers. These are all kind of trial and error for each game, depending on what you kind of make. You'll have to sort of tweak around to figure out where you want to put the score and the various other icons. So these are all sort of statically defined in here. Feel free to obviously change anything you like. Most of it is kind of coded in a way that should be able to be updated from the header file for most things. So I'll look at 2 sort of states here just to go through quickly before I kind of wrap up the video. We'll go through new level here, and I'll tell you the difference between new level and reset level. So let's drag this over here so we've got more room. So here we go in new level. I'll just delete this old code as that's not needed. So let me see, we don't need any of that either, so I'll get rid of that. That was just a previous way to draw the title. So every time there's a new level, we have to tell the level manager to set the new floor graphics. That basically draws everything to the backdrop. Just draws new floors. So if you're wondering what that does, that's just this here. You could obviously remove that and put whatever you want in. It could even be just put as part of the initialized level code, really. And then we plug in the game's level into the level initialize. That obviously reads the level arrays and plots everything for us. We can then call player initialize and baddie manager initialize. That's both of those then set up, ready to be used. We then set the next state we want to run, which would be the get ready state. And then when that state first runs, it then gets trapped in here. So it then updates the substate to the next one, and then it sets the end state to false, and then it then sets the timer for the miscellaneous timer here. This is basically a timer for how long this state will actually be running before it automatically ends if the player does nothing. we then have to tell the message manager what message it should be working with next. We then reset the input manager so we don't get any false key presses. Maybe the player pressed a button from some other part in the game. Obviously now we want to forget everything before this state. So if the substate is not to initialize, then we can update the miscellaneous timer, and we also check to see whether the player has pressed a button to skip the get ready state. And then in each state we always need to redraw everything still. And the reason for that is the display is obviously not static. The frame buffers aren't static. You have to repaint everything over and over again. So everything's kind of on its own layer, if you like. So you have to redraw everything over and over again for each state. And then at the very end of the state, we check to see if the end state is triggered by either the miscellaneous timer or the player has pressed the button. If it has, then we set the substate to initialize again, and then the next state to play. So each state pretty much should have, or could have, almost identical stuff in it. But that also means you could have unique drawing code for each different state. And then this function here, this just updates all of the information for the player. So we print the title in game to say what game it is, and then we literally draw all the important information the player would want to see. Score. And then one thing to note here, which you might find to be strange, is why these symbols are plugged in here. So I'll quickly explain that. So in this font set here, you'll see we have this heart. So this font set is 8 by 16 pixels in size. So half of that heart is a star and the other half is a hash, which is what we're doing here. We are literally drawing those two tiles there and then printing the numbers out there. That's what that's actually doing, if you wondered what the hell was going on there. And then that's oh yeah, the new level. I didn't actually put, oh no, yeah, is that actually called? I'm not sure. Level clear. Yeah, that's fine. Like I was saying, most of these are pretty much the same. You just want to plug in a different message. So by all means, play around and experiment. That's all I can say really to get to grips with any more of the things here. Let's just double check that this actually works. before I finish up. There we go, so you can see things in action there. For your own version of this or tweaks, might want to change some of these timers, maybe you don't like that, or switch out the font set to something else possibly. There's nothing too much going on here, I don't think. It's pretty much the enemy code is kind of just the same as the players to some degree really. The only thing that might appear a bit weird is how the collisions work. So I'll quickly talk about that. So to check how the player collides with the enemies here, we have the baddie manager overlaps function here. You just put in player's rectangle, which you can get by calling this function here. So you see the player code never actually includes the baddie code, and likewise and then internally in the enemy manager here, let's have a look here, see if there's anything interesting. Oh yeah, internally there's like another function for checking the overlaps here. You see that there's two of them. There's this one here which is used for the player, and then there's this one here which has the main code in and is used internally by the baddie manager here. So you'll see that it takes an integer ID here, and this is, we want to know which enemy is asking whether it's collided with the others, because obviously we need to skip over checking the collision between itself and itself in this list, otherwise that will cause bugs. That's why this function here exists, so we can use it for the player as well as the enemies colliding. So with regards to the player, we pass in a negative number because this integer will never match any of the actor numbers, because we use the start ID to compare with the actor ID here. So the start ID is where we start in the enemy array, and you'll see we have a rectangle which we take from this pointer, and then we first check to make sure the actor ID is not equal to the start ID. Again, this is so that the enemy isn't checked with itself for a collision, and then by plugging in the player's one with this as well, this means the player never interferes with any of the enemies in the list as well. Other than that, there's nothing magical going on. The enemies also have a state manager in them as well for whichever way they're facing. So I think that wraps everything up. If you've got any more questions on this, then leave them in the comments below. Hopefully this will provide you with a decent whole game to kind of get into playing around and toying around and working on the 3DS. Right, that's it for this video. In the next video, maybe it's going to be sound, or maybe it's going to be a step into 3D graphics. Let me know in the comments which you would prefer next, and I will catch you in the next video.